with a situation like my indent, I made my reference pattern out here in a corner, out in this corner here, where I'm far from any strain. And so I can make the assumption that at that reference point, the lattice is undistorted, unstressed. That works fine here. This is looking at thermal strains around an inclusion of carbide in the superalloy. If I take my reference point far enough away, it's fine, it's just driven by the thermal expansion of this mass. If I'm looking at a crack tip, here's a fatigue crack tip. Again, if I go remote from the crack tip, that's fine, it would be strain 0, and so I can work out what the variation is and get the absolute values. But not everything's like that. Take a polycrystal deformant. There are strains everywhere, and that's kind of what we wanted to know about. And unfortunately, I don't know what the strains are at the reference point. One of the get rounds, well, why we got interested in geometrically necessary dislocation densities, in part was a get round of fudge, an avoidance of the real issue of trying to work out what the reference state was. So you can learn some stuff. You can make comparisons to simulations, so you can do a deformation experiment. Here again, this was looking at the inclusion problem in a superalloy, but imposing some mechanical load over the top. And then we don't know anywhere in that map what the strain is from the measurements. But we can do a simulation. We can do a crystal plasticity simulation and learn what we expect the mean, the field within this whole patch to be, and superimpose that on as a mean. Or, in this case here, again looking at a misfitting layer sample, you can make an X-ray measurement to get the average value and impose that on top of the variation within the field. So they work kind of okay, but it's not quite satisfactory. I'd like to be able to do it properly. And one of the things you think about is, well, can I use a simulated pattern as my reference? So we looked at this with Claire Maurice and others at Saint-Etienne. Here's an experimental pattern from germanium. Here's a dynamical simulation that comes out of Wilkinson's code. And here's a kinematic simulation. And I think visually you can see that these two look kind of similar. That, well, it's got the right bands in it, but it's not really got a proper match. If you make cross correlations between these two at different boxes in here, the arrows in here show the measured shift. And if we look at this one here, the kinematic simulation, the trouble is there are some points in here where there's really big shifts because the simulation isn't really a good match to this. It's got a low fidelity in how it represents the intensities in here. And so these erroneous points in here, you can see the arrows are pointing kind of not in a smooth field at all. This really doesn't work. It's not a good enough match to the intensities in the experimental pattern. We can't use that. I've put up here on, can we use the dynamical simulation? Well, maybe. The field displacement looks smooth, at least, which I'd expect it to be. It looks kind of reasonable. The problem is, I don't know the geometry well enough of my detector when it comes down to it. And you can have a look at this just by thinking, well, what would happen if I didn't know the detection position in here, if I just knew my camera length and camera pattern center position to plus minus 0.5% of the camera width, a few pixels in other words, what does that mean? Well, it means that I get pattern shifts potentially by a few pixels that are uncontrolled. And if I've got a few pixels in the pattern shift, that means I've got strains when I calculate them through to 10 to the minus 3, and could well just dominate anything that I'd see. So, unfortunately, no, we can't use the simulations. Well, I say that,